finding a limit as x goes to infinity. What does this even mean? Well, I hope to show you in this video. So when we find the limit as x goes to infinity, that means we are looking at something called end behavior, or what happens to the far right of the graph as x goes towards positive infinity. So just keep that in mind. This is all finding end behavior. So with any limit problem, the first thing we should do is think about directly substituting in my limit value, in this case infinity. So if I take 2 times infinity squared plus 3 times infinity, well, I'm going to get infinity in the numerator. In the denominator, 4 times infinity squared, well, it doesn't matter what I subtract. If I'm subtracting 5 times infinity plus 1, if I've already done 4 times infinity squared, that's already a huge number, which is also equal to infinity. So you get something that looks like infinity over infinity, and you may be wondering, what does infinity over infinity equal? In this case, we have to come up with a different method in order to find this end behavior value. So what we do for limit as x approaches infinity problems is you're going to divide by the largest degree in the denominator. In this problem, you can see the largest degree is x squared. So what that means is I'm going to go through and divide every single term by x squared, since x squared is, once again, the largest degree in the denominator. Now let's simplify. This would simplify to the limit as x approaches infinity of 2 plus 3 divided by x, all over 4 minus 5 divided by x, plus 1 over x squared. Now we want to think about directly substituting in infinity again, but now with this new form. As I look at the number 2, well, that's going to say the number 2, but as I plug in infinity to 3 divided by infinity, I have 3 divided by an enormously huge number. Any number divided by an enormous number is going to approach the number 0. So that's why 5 divided by x is also going to approach 0, and 1 divided by x squared is also going to approach 0 because it's going to be a number divided by an enormous number. So let's take a look at what we have left. We have 2 plus 0 divided by 4 minus 0 plus 0, or 2 divided by 4, which reduces to 1/2. So the limit as x approaches infinity of this rational function is equal to 1/2. Once again, this tells you about the end behavior. I'd love to show you the graph so you can see a nice visual of what's going on. So as we look at the graph of this rational function, you can see as x approaches infinity, which means as we go to the far right of the graph, you can see the graph approaching the value of 1/2, or positive 1/2 is a horizontal asymptote. Let's go ahead and try another one. But if you're finding this video useful, make sure to click subscribe in the lower right-hand corner so that you can see new videos as they come out weekly. Here we have another rational function, and it's the limit as x approaches infinity. Once again, we talk about dividing by the largest degree in the denominator, because if you were to plug in infinity, you would again get infinity over infinity. This time, the largest degree in the denominator is x cubed. You can see that right here. So I'm dividing every single term by x cubed. Simplifying, we have the limit as x approaches infinity of 5 divided by x squared minus 1 over x cubed, all over 2 minus 3 over x cubed. Now think about plugging in infinity. 5 divided by an enormous number, 0, 0. All of those approach 0. So what do we have left? 0 minus 0 over 2 minus 0, which simplifies to 0. So it looks like for this rational function, the end behavior is 0. Again, let's take a look at the visual. Here's the graph of this rational function, and you can see as x goes forever and ever and ever to the right, that the graph approaches the y value of 0. Let's take a look at one more example. Again, we have the limit as x approaches infinity, and if you were to plug in infinity, you would again arrive at infinity divided by infinity. So we're going to divide by the largest degree in the denominator, which you can see in this case is only x. Simplifying, I have the limit as x approaches infinity of 2x minus 3 divided by x all over 5 minus 1 divided by x. Now go ahead and plug in infinity. 2 times infinity minus, well, this would approach 0. So 2 times infinity minus 0, well, that would be infinity. And on the bottom, 5 minus 1 divided by infinity would approach 0. Infinity divided by 5 is infinity. So it looks like this time the limit is infinity. What does this graph look like? Let's take a look. You can see here the end behavior, or as x approaches positive infinity, this graph is approaching infinity itself, or rising without bound. So in summary, I want to look at a little shortcut we may have noticed and we may use. Let's go back to the very first example. In the first example, look at our degrees. The degree in the numerator was equal to the degree in the denominator. When that happens, the limit is equal to the ratio of the leading coefficients, or 2 divided by 4. That's when the degrees are equal. When the degree in the denominator is larger than the degree in the numerator, your limit will always equal 0 as long as x is approaching infinity. And then the final shortcut is if the degree in the numerator is larger than the degree in the denominator, the limit as x approaches infinity will always be infinity. I hope you found this video useful and also those shortcuts useful. And if you did, please make sure to click subscribe so that you're notified when new weekly videos are posted. Thank you for watching.